It was the heroic age of science. Within 60 years, we had discovered the first law of electrodynamics, put forth the theory of evolution and the germ theory of disease. We had established absolute zero and come to understand that electricity and magnetism are not two separate forces, but simply different manifestations of the electromagnetic field. We had begun to unlock the secrets of radiation and to speculate about the atom itself. But in 1905, one man would top it all with what will forever be known as the Annus Mirabilis, the miracle year. In 1905, Albert Einstein changed the way we think about physics forever with 4 extraordinary papers. Each on its own could have been the achievement of a lifetime for anyone, but this humble patent clerk gave us all 4, one after another. His most famous papers are perhaps those on relativity, the first of which, special relativity, showed us that the speed of light in a vacuum is fixed, not dependent on the motion of the light's source. And from these complex workings, we would get the concept of space-time. The idea that, just as electricity and magnetism are one thing, space and time are one thing, and can affect each other. Meaning things like gravity and speed can distort time itself. It's where we get all those fun ideas science fiction loves to play with, like the fact that time goes slower for someone traveling near the speed of light. The second of these relativity papers, general relativity, gave us the most famous equation of all time, E equals mc squared. The seemingly counterintuitive idea that mass and energy are interchangeable, that objects, just by existing, have energy. Not potential energy, not kinetic energy, but the energy of their mass. It's the reason why when we split an atom, an incredible force is let loose. Then there's his conceptually simplest paper. For decades, a strange physical phenomena had gone unexplained. A delicious-sounding phenomenon called Brownian motion. You see, there was this guy named Brown, and when he was looking at tiny grains of pollen suspended in water, he noticed that, no matter how still he tried to make his slide, the pollen grains would jitter. They almost seemed to randomly walk around the droplet. And just to make sure it wasn't some odd property of pollen, he tried this with other things, including a piece of the Sphinx. You know, just to be thorough, I guess. And yup, even the Sphinx did that weird little dance. No one could figure out why this happened until Einstein showed fairly conclusively that Brownian motion, as they had come to call it, had to be the result of all of the surrounding water molecules and their constituent atoms jostling the much larger specks of pollen. While this may not seem like a huge revelation to us today, at the time, there was still a lot of debate on whether or not atoms were a real thing. But the math in this paper not only proved that they were real, it even gave scientists a way to derive how many atoms were in an area through careful observation of Brownian motion. But it's really Einstein's other paper that I want to talk about today, the first of the 4 he actually released. It was his most controversial work at the time, and its ramifications challenged even his understanding for the rest of his life. This is the paper that he won the Nobel Prize for, his paper on the photoelectric effect. This is the one we touched on last time, where he demonstrated that energy comes as quanta, that it doesn't come in a flow but in discrete packets, that it's not like a stream of water. This idea flies in the face of classical physics. Maxwell, when establishing electromagnetism, had shown the wave-like properties of light. So how could something wave-like only come in discrete packets? Even Planck, the very man who had, reluctantly, introduced the world to the possibility of energy being quantized, once introduced Einstein by saying, "He had done so much for physics, we should forgive him for being overzealous in thinking the photon was a real thing." But Planck wasn't the only skeptic of note. There was another by the name of Niels Bohr. Bohr's early life couldn't have been more different than Einstein's. Where Einstein was poor, Bohr was wealthy. Where Einstein's father came from a failed business, Bohr's was one of the most connected in all of academia. Where Einstein struggled at school, Bohr excelled. But with such different backgrounds, it makes sense that these two men, these two friends, came at the problem of the quanta differently. When Einstein proclaimed the quanta's existence to the world, Bohr at first rejected it. But once Bohr did embrace the idea of the quanta, He embraced it fully, taking it further than even Einstein was willing to go, chasing it to its logical extreme. You see, at this time, the scientific world was still struggling with the concept of the atom. Einstein had helped to establish that atoms existed, but what were they? What did an atom look like? What was the physical model for it? How did it work? Well, Bohr made his name by giving us a new model for the atom. It's the one you probably learned in high school. And though we've actually developed a far more accurate model for it since, Bohr's model is still one of the easiest to understand. In his model, electrons orbit the nucleus of an atom like planets around a sun. Nice and simple. People had considered similar possibilities before, but Bohr's big innovation was realizing that if energy comes in quanta, which is to say, discrete units, and electrons' orbits are dependent on their energy state, then electrons orbiting a nucleus could only exist at very specific distances from that nucleus. They couldn't just be wherever they wanted. This is where we get those concentric rings of electrons around the atom that you probably saw in high school. But there's an issue with that model, something that they probably tactfully glossed over in your high school science class, and you might have already guessed it. So if electrons can only exist in fixed orbits at very specific distances from the nucleus based on the quanta of energy, and if, when an electron loses or gains energy, it moves to a different orbit, how does it get there? Like we established, they can only exist at fixed distances from the nucleus, not anywhere in between. So do they teleport? What is this bizarre quantum leap they're taking? Well, now everyone had to start figuring that out, because Bohr's model fit with a lot of what was being seen experimentally. And this led people to follow that rabbit hole to its extreme. People started to conjecture that if light can act like a particle and a wave, maybe matter can too. And if we accept that, then we have to start seeing not just light, but the entire world as probabilistic. We can start looking at events as waves of possible outcomes that collapse into a single reality when they are observed. And when we start doing that, weird stuff starts rolling out of our math. It's from here that we get the famous uncertainty principle, which states that the more we know about one complementary property of a particle, the less we can know about the property it complements. For example, take position and velocity. The uncertainty principle says that the more we know about where a particle is, the less we can know about how it's traveling. And if we accept that, this idea that we can't actually know all properties of a given system at a given time with absolute certainty, it's just a tiny leap from there to say physical systems don't exist in states of absolute certainty, just in a space of possibilities with more or less likely outcomes. That there is no underlying absolute reality for us to ever get a hold of. Just gotta breathe for a second. And it was this last idea, that last leap of logic, that Einstein couldn't abide. He, who had pushed so hard for the photon, and had so often been met with derision from his fellow scientists because they rejected a notion that fundamentally broke their understanding of how the world worked, was now doing the same thing to the next generation of physicists. But he had a point. Could quantum mechanics actually be considered a complete theory if it only dealt in probabilities? Didn't there have to be something underlying it all that our probabilities were describing, but that we had yet to completely grasp? Wouldn't it be a disservice to science just to accept that this was the way the world worked and look at things probabilistically rather than dig into the reality which Einstein so ardently believed these probabilities had to spring from? Well, at the Solvay Conference in 1927, as the greatest minds of a generation looked on, Einstein and Bohr, these two titans of physics, these two friends, would debate just that. So join us next time for the Einstein-Bohr debates and the conception of our world that came out of them.